what is energy of a dipole in an electric field? If a dipole is there in the electric field, it experiences torque. Let us assume only one special case. If there is a uniform electric field E, if there is a uniform electric field E in this region, there is a uniform electric field, there is a dipole, and the dipole moment is from negative charge to positive charge. Let us assume minus q over here and plus q over here. The direction of the electric dipole moment is a vector, that is q into 2d. It is q into 2d. Its direction is from negative charge to positive charge. See, here the lines of force are going in this direction. That means that on this side there will be lots of positive charges and there will be uniform distribution of lots of negative charges, and the direction of the electric field is in this direction, electric field's direction. See, if then naturally the force will be on this side and the force on this will be this side. It makes already an angle theta. So let's say this is the midpoint, the total distance between the dipole is 2d, and this is the midpoint here, and it makes an angle theta. You would like to rotate this. Rotating, how do we do that? Already force is on this side. If the external forces are acting on this dipole, to rotate this, it's an external torque, right? So in order to rotate, you need to exert torque. In order to push this, in order to produce translatory motion, you need to apply force. In order to produce rotatory motion, you need to apply torque. If you want to rotate this, at this point, if the angle is theta and the dipole moment is p, in the last section we have derived that torque acting on a dipole is P cross E. If you would like to find only the magnitude of the torque will be Pe sin theta. Hence, if you want to rotate this by a small amount d theta, then the same amount of torque what is experiencing here, the same torque you need to apply. So by applying a torque of P sin theta in the opposite direction, d theta, if you would like to rotate, we know that work done is force into displacement, and if the displacement is theta, then this distance is r, this is theta. So work done is force into displacement in linear motion, work done is torque into angular displacement in the rotational motion. Then through a small angle d theta, the net work, the work done is small work done dw through a small angle d theta. Then the torque at that instant is Pe sin theta d theta. Then the work done will be Pe sin theta d theta. This means that in order to rotate through a small angle d theta against the electric field, the amount of work that you do is Pe sin theta d theta. What is the electric field? What is the work done by the electric field? Work done by the electric field will be negative of Pe sin theta. The negative of Pe sin theta is the energy, that we have taken it to be plus is dw, which is what? Du, energy. Then the total work done or total energy of the dipole, since we have taken it to be the work done by the external torque by plus itself. If you consider work done as a negative thing, then minus of minus will again be plus. Then energy of the dipole is the external work done, because when you do work on the dipole, that work energy is stored in the dipole. Hence, work done by the external force or external torque is P sin theta d theta. Then the total energy will be sum of all the work done, external work done. So integral P sin theta d theta. P is dipole moment, so which is small p can be taken out, E taken out, because in a uniform electric field, I said it's an electric field, it's a dipole in a uniform electric field. Hence it is P sin theta when you integrate it minus cos theta from theta 1 to theta 2. Suppose theta 1 to theta 2. So the energy of a dipole is minus P cos theta, and whenever theta 1 theta 2 you apply, from theta 1 to theta 2 you will get work done. What is energy of a dipole? Energy of a dipole is minus Pe cos theta. See what happens, you please try to understand this. If there is a dipole and this is negative charge, this is positive charge, the dipole moment will be this way, negative charge and positive charge. If the dipole is along the direction of the electric field, theta is 0. If theta is 0, cos 0 is 1. energy is minus PE. Then if you rotate the dipole perpendicular to the electric field is in this direction, then theta is over here. I mean dipole moment is from negative charge to positive charge upwards. The angle between them is 90 degree. So PE cos 90 degree is 0. When the dipole is aligned along the direction of the electric field, its energy will be minus PE. When the dipole is perpendicular to the electric field, energy is 0. When the dipole is aligned opposite to the electric field, energy is PE cos 180 degree. Cos 180 degree is minus 1. Minus of minus 1 becomes plus 1. So here it is PE. So when the dipole is against the electric field lines are this way, dipole moment, negative charge over here, positive charge over here. So the energy it has is plus PE. So when it moves from here to here, it will lose PE so that its energy becomes 0. Then when it goes from here to here, it loses even more energy PE, so its energy becomes minus PE. So when you move from here to here, by rotating the dipole from here to here, you have to work, or you have to put in a work done which is equal to 0, I mean minus PE to 0, 0 to PE. So PE plus PE 2PE. So the energy difference between this orientation and this orientation of the dipole will be 2PE. This is what happens in say microwave oven. So rapidly changing electric field will turn the water molecules here and there. By moving from here to here, there is a difference in energy of 2PE happens. That energy will be dissipated, that produces so much of energy. That is from where you are getting heat in the microwave oven.